In today's video, we are designing a grid-connected inverter with the following parameters: nominal power 100 kVA, input voltage 800 volts, DC, switching frequency 10 kHz, resonance frequency 1 kHz, and the nominal frequency is 50 Hz. In designing our filter, a 10% ripple of the rated current has been considered. The VDC has been selected as 800 volts. After the calculation gave us 816, so we selected the closest, which is 800 volts. Remember, the modulation index MI is selected as 0.8, and remember it shouldn't be above 1. To calculate the inverter side inductance L1, we use the following formula, and the value of the inductance L1 gives us 500 microhenry. And L2 is a function of the inverter side inductance, which gives us 0.3 times L1, giving us 150 microhenry. And to calculate the total inductance, we calculate total inductance as L1 plus L2, which is equal to 650 microhenry. The value of the capacitor CF is given by 0.3 times C base, which gives us 100 microfarad. In this design, we are using the IGBTs. You can use the MOSFETs. And using the connection ports, we can connect our VDC plus VDC and minus VDC. We can also label our phase voltages as VA for phase A, and VB for phase B, and VC for phase C. So we are using the connection ports because we want to create this inverter as a subsystem. We can now save our work. Okay, now we create the subsystem for the inverter. There you go. We can delete this. We set this to the right side, the VA and VB and VC, so that we have them on the right side of the subsystem. Our DC input voltage is 800 volts. From the inverter side, we get the current measurements. So we are using the three-phase voltage current measurement circuit. We now implement our LCL filter. Our L1 is set to 500 microhenry. And our L2 is set to 150 microhenry. With the capacitance connected in parallel, which is 100 microfarads. We take the voltage measurements at the grid side. We set the parameters for the grid as follows. So the measured voltage, which is in the ABC reference frame, is converted to the alpha beta, and then later to the DQ reference frame. It's converted to alpha beta so that we generate the phase angle theta. The phase angle theta is used for synchronization of the grid and the system. and the current at the inverter side is converted from the ABC reference frame to the DQ reference frame. We can now design the phase locked loop, or the PLL. To get the phase angle ranging from 0 to 2 pi, we can wrap up this using the mode and the 2 pi. So you connect the mode and 2 pi there, and you can get a sawtooth signal ranging from 0 to 2 pi. So our angle omega t is now applied to the alpha beta to dq blocks. We now design the current controller. We're setting our reference current to 200 amps. And using the summation block, we compare the reference current to the measured current ID for the D-axis and IQ for the Q-axis. And the obtained error is applied to the PI controller for both the D-axis and the Q-axis. The DQ parameters are now converted from the DQ reference frame to the ABC reference frame. Then they are applied to the sine pulse width modulator. So the sine pulse width modulator generates the switching pulses S1, S2, S3, S4, S5, and S6 for the inverter. I decided to design a 100 kVA inverter to compare with a 10 kVA inverter. So I wanted to see if the parameters can just be multiplied by a factor of 10. Since initially we designed a 10 kVA, now we've designed a 100 kVA. Sets the parameters just by the ratio of 10 since we've increased the power by 10. Since initially we had 10 kVA, now we have 100 kVA, are these other parameters just going to be multiplied by a factor of 10, such as the filter design? Initially, if you had 10 millihenry as your inverter side inductance, now that you're designing a 100 kVA, are you going to have 100 millihenry for the filter, and is the system going to still work the same? So as you can see from this system, we can't just get the parameters just like that. Since we designed a 10 kVA with L1 equal to 9, it doesn't mean that this one we're going to have L1 as 90 and the system is going to work. No, this is a non-linear system, and most of the parameters, if you look at even the PI controller, it also had to change accordingly. You may not just get a 100 kVA and just adjust the parameters to suit a 10 kVA implementation. You need to redesign all these other parameters, like the filter design and the PI controller design will be different. So now when we set our reference current to 200, we see that after we run our system, we are getting 200 amps. So if you want to check the behavior of the PI controller, you can compare the reference current and the measured current. So you connect one leg to the reference current, the other to the measured current, and the other to the output, which is the error that you are getting. Shall we start with setting the Kp and Ki to 0? So as we can see from here, we can see that this basically means that the current controller is absent. The waveform is well controlled by the grid, but definitely we see that the current waveform requires a controller. We now set the Kp and the Ki to 1. Beautiful. We see the perfect waveform for both the voltage and current waveform. Wait a minute. Is it really a perfect waveform for a current waveform? I don't think so. Look at our reference current. It's 200 amps, but we are getting 400 amps. This means that definitely something somewhere is wrong. So when we check the PI controller in the Q axis, we see that there we have an overshoot in the waveform, and it takes a lot of time for the waveform to settle down or for the signal to settle down. So we really need to adjust our integral gain. So is the case even in the D axis. We see an overshoot, but the controller is taking time to stabilize. Okay, so now we increase the value to 10, the integral gain to 10. Okay, so it's stabilizing. Okay, not really stabilizing as we can see. So we still have a lot of oscillations, and the signal is taking long to stabilize. So let's now try to change. We increase the integral gain now to 100. There you go. You see that the signal now is stabilizing a little bit faster. That is, you see at 0.02 seconds, the signal stabilizes and it maintains that stability. But I don't like the starting overshoot there. It's still taking a little bit more time to stabilize, as you can see even in the current waveform there. So we adjust again, adjust the integral gain to 1000. Let's see what we get. Okay, there we go. At least the signal stabilizes faster despite having an overshoot. So we adjust now to 10,000, the integral gain. Let's see what we get. Okay, so here at the beginning we have a lot of oscillations. This is not good. So since we're having oscillations, can we adjust the proportion again? Because when you have a lot of oscillations in the signal, you have to adjust the proportion again. So if we adjust the proportion again, we see what we are getting. If it's not okay, then we can just settle for a proportion again of 1 and the integral gain of 1000. So there you go. Not very bad. The overshoot is reduced, but you have a lot of oscillations, as you can see in the signal. Our waveform has a lot of oscillations. So we can just settle back or just go back to 1 and 1000, as in Kp equal to 1 and Ki equal to 1000. Don't forget to subscribe to this channel so that you can get more videos like this. And I would be very grateful if you liked the video and shared the video. See you in the next episode, and bye-bye.